Hi, I'm Tara Blevins, and I'm going to be talking about our work on gloss-informed bioencoders for word sense disambiguation. So word sense disambiguation, or WSD, is the task of picking the specific meaning or sense that a polysemous word takes in a given context. Performance on less frequent senses of words in WSD tends to be much worse than on the most common senses, since these uncommon senses have fewer training examples in WSD datasets. To address this performance disparity on uncommon senses, we propose gloss-informed bioencoders, which incorporate sense glosses and pre-trained encoders into a WSD system. The gloss-informed bioencoder contains two encoders. The first is a context encoder, which takes in an ambiguous word and its surrounding context and produces a contextualized representation of the ambiguous word. The other encoder is the gloss encoder, which independently encodes the definition of each candidate's sense of the ambiguous word into a sense embedding. The bioencoder then chooses the sense embedding that has the highest dot product score with the contextualized representation of the ambiguous word as the disambiguated sense. Our experiments focus on the English all words disambiguation task, where we train the model to disambiguate every ambiguous word in a given context sentence. We compare our bioencoder model with a simple linear word sense disambiguation classifier trained on the output of a Rosen-BERT encoder. And as shown in the table on the bottom left, we also compare our model against prior work that has considered other methods of using definitions and pre-training to improve word sense disambiguation. We find that our full bioencoder model outperforms the next best performing model by 2 F1 points with an overall performance of 79 F1. And when we break out performance of the bioencoder based on sense frequencies, we find that it performs similarly to the baseline and the previous model on the most frequent senses of words. Instead, the performance gains we see in the bioencoder almost all come from better performance on the less frequent senses, with a 15-point F1 improvement on that subset over the next best model. For the zero-shot examples in the evaluation set, where the senses in these examples are never seen during training, we see a similar trend. This shows that the bioencoder has learned to generalize to completely unseen senses as long as it gets a definition of this new sense. And finally, we looked at how effective the bioencoder is at learning from limited data with a few-shot learning setup. As shown in the graph on the right, we found that the bioencoder is much more data efficient than the Rosen-BERT baseline, and is able to achieve similar performance to the full baseline model when only given 5 or fewer examples per sense. So, in conclusion, we see that the bioencoder model improves over our baseline and previous approaches on English all words word sense disambiguation. And from our analyses, we show that these gains come almost entirely from improved performance on less common senses of words. If you have any questions about this work, please feel free to email me or to check out the GitHub repo for this project.